Welcome everyone. Thanks so much for the invitation. It's a pleasure to be here. So I know that many of you can be from slightly different backgrounds compared to me. So we'll go slow initially, and whatever I say, if anything is unclear, just feel free to kind of interrupt me and tell me this. It doesn't make sense. So my plan essentially is to talk about advances over the past decade, in some sense, on some specific problems related to unsupervised learning. And it's a very personal opinion that the best way to somehow see all these techniques in play is to see them in the context of specific examples. So what I'll do essentially is that I'll introduce certain canonical examples, and I'll build up all the techniques in the context of these examples, and I'll apply them to these settings. Okay, and I should say one thing, which is there's lots of seats here. So let me say something that to keep our discussion quite informal. I'll not refer to specific references at every step, but if you're interested about the original references and where things started, just reach out to me. I'm happy to share the original papers and stuff. Okay. So what is the plan for today? So I'll start with the examples. And I think it'll be important for us to really understand these, because whatever we do in the remaining lectures will be in the context of these examples. I'll introduce what are the main statistical questions, statistical and algorithmic questions. And towards the end, I want to talk briefly today about some information theoretic ideas. Notions. So these information theoretic notions essentially are very useful to establish fundamental barriers to signal detection and recovery in these particular examples. But we'll come to that in a bit. Okay, so let me jump into the examples. And the first one I'll start with, this is by now very well studied. It's this problem of community detection. Okay, so what is the problem here? The problem here is that we get to see data, which is a graph on n vertices with some edge set. So here n is just the set 1 to n. Right? So I have a graph on n vertices. I've just enumerated them 1 to n. And sort of the idea is that you have this graph, and there's some, let's say, underlying partition. Edges are more likely or less likely, let's say more likely within the members, within each group, and sort of less likely across the partitions, right? And statistically, the question is, okay, given this graph, can you recover, or how well can you recover this underlying clustered structure? Right? That's sort of the basic problem. Okay. So let me not go below this. Okay, so how do we formalize this question? So we will formalize this in the context of a probabilistic model for the graph. And let me start with sort of the simplest variant of this model. This is the so-called stochastic block model. Okay. So what we do here is the following. There is some underlying vector sigma, and each sigma I is IID plus 1 or minus 1 with probability half each. Okay? So you should think of this vector sigma as essentially encoding the true underlying clustered structure of the nodes, right? So if sigma is plus 1, then I'm in group 1. If it's in minus 1, then I'm in group 2. Okay? And then given sigma, what we do is that we fix two numbers Pn and Qn in 0, 1. And then we add our edges with probability Pn if sigma I is sigma j and is Qn otherwise. Okay? So this is our model for the data. We first generate these true underlying assignments. We'll call this the community assignments, let's say. And then we add our edges with these probabilities depending on the true assignments. Okay? Now, typically, just to build up some intuition, the setting, okay, where Pn is bigger than Qn, this is sort of the more natural setting to think about. People often refer to this as the assortative case. And if in fact, Pn is less than Qn, this is referred to as the disassortative case. But this is just terminology. The intuition sort of is that you have individuals that can be in two different groups. And in the first case, you're more likely to have an edge between two individuals that are in the same group. Okay? But mathematically, you can consider both these possibilities. Okay? Okay. Any questions about the model? Okay. So we'll make this more precise as we go along, but the main target is to detect and recover sigma from the graph G. Okay? Now, I put these in quotes here because, okay, it is somewhat intuitive what we are trying to do, but we'll make this much more precise as we go along. Yeah.
So is there any reason that the sigmas are like chosen randomly, or like that could be just?
Okay, great question. So why? So in some sense, I take them to be kind of equally likely in some sense, because this is kind of the most challenging setting. For example, if you had one group that was kind of 90% common and the other group was only 10% of the vertices, then if you asked me to guess, I would guess group 1 and I would get it right most of the time, right? So if it were like one very rare group and one, I mean, okay, you can still ask, okay, can I do better than random guessing? That's kind of a second order question, which is still interesting. But in this context, this is kind of calibrating it at a level so that if I guess randomly, I'll get 0 accuracy on average. And so we'll pose the question, can we do better than that?
And this explains why this is balanced, but why this is random? Is there any reason for that?
Oh, no. Yeah, so that, right, okay. good. That's the second half of the question. So turns out you can, for example, look at worst case community structures given that they are balanced or approximately balanced. Effectively, it turns out that this is in some sense the least favorable prior for this problem. So putting a uniform assignment is sort of what the adversary would do if they were choosing things adversary, if they were choosing it in the worst case. But you're right. I mean, in terms of setting up the problem, I could have as well considered an arbitrary underlying configuration sigma that is balanced. But I want to sort of pose a follow-up question moving forward for which this particular formulation will be a bit more useful. But okay. Okay. Other questions? Make sense? Okay. So maybe to just say one comment about this particular model, the Vluk model and the associated community detection question. This has a very long and rich history. It started in the social sciences back in the 80s. It has been looked at extensively in statistics and computer science. In computer science, it has come up in the context of discrete algorithms, like problems where you try to find bisections of graphs. So this has been investigated from many different perspectives. Let me make one comment here. So in this lecture and sort of in all the remaining ones, I'll kind of restrict myself to a very specific scaling regime for these probabilities. Okay? So I'll talk about this particular regime where Pn is of order A over n and Qn is of order B over n. Right? Here A and B, they don't come subscript, they don't have subscripts n. So what I wish to convey here is that these are fixed constants independent of n. Okay? And this will be our scaling regime throughout. So the reason why I restrict myself to this case is that, as you can imagine, these probabilities essentially govern how many edges are present in the graphs, right? And turns out the average density of the graph really governs the behavior of the problem. Okay? So in certain cases, if you have more edges, you can strive to do more. But this is sort of a regime where you don't have too many edges. If you look at the degree of a typical vertex, that's kind of fixed. So this case presents some interesting challenges and kind of exhibits most of the phenomena that I want to talk about. So I'll restrict myself to this setting, but I want to remark here that all the other scaling regimes on the probabilities, they have been explored, and we understand what happens in these cases. But for our discussion, I'll restrict myself to this case.
Sorry, I missed it, but can you actually tell exactly what kind of answer are you expecting?
So I'll get to that in a bit. Yeah. So my plan is to first talk about a couple of more examples, and then I'll really formalize, what is my target, what I mean by detection, what I mean by recovery, what kind of questions I'm looking at. Yeah, I'll get to that in a bit. Hopefully within the next 10-15 minutes. Okay. So let me talk about the second example. So this I'll refer to as Z2 synchronization. So this looks similar to the first example. In this case, our data is a matrix M, which is an n by n symmetric matrix. Okay. And how is this data actually generated? The first step is similar. So I have some vector sigma. The sigma I are IID plus or minus 1. And then the matrix is essentially a rank 1 deformation plus noise. Okay? So here lambda is a positive constant independent of n, and W is a noise matrix. So W is W transpose, and if I look at Wij, these are IID normal 0 1 over n for I less than j, and normal 0 2 over n if I is equal to j, and everything is independent. Okay. And the target again, and as I mentioned, I'll make this precise, but the target is to recover sigma from M. Okay, let me pause here for a second to see if there are any questions regarding the model itself, and then I'll talk about the motivation and this scalings. Okay, so let me add some remarks about the model. The first is a question about normalization. So you might say, okay, these scalings kind of seem funny to me. Why do I have a leading 1 over n factor here? Why do I have, why are these variances scaled to be of order 1 over n? Why are you setting these up in this specific way? So in some sense, how I like to think about this problem is that this component is essentially the signal component, and this is noise, right? And so to kind of see the competition between the signal and the noise, what you want to do is to ensure that the signal and the noise are on the same scale. If the signal is too big compared to the noise, then your problem will become trivial in some sense, right? So how do we measure the strength of the signal and the noise in this problem? We essentially measure it in terms of the operator norm of these matrices. Okay, and the scaling, for example, ensures that if I look at the usual L2 operator norm for this matrix, then this is order 1. Okay, in fact, we know much more about this, but this scaling ensures that this is on the scale order 1. And if I look at the operator norm of the matrix 1 over n sigma sigma transpose, this is of course the L2 norm of the vector sigma, so this is also order 1. Okay, so this scaling essentially ensures that everything, the signal and the noise are on the same scale, so they actually compete, and we'll see non-trivial phenomena. Any questions? Yeah.
So why it seems like noise is diagonally dominant?
No, it's not actually. Okay, so good question. Why is this 2 over n? So turns out that this isn't actually diagonally dominant because you have far fewer diagonal entries in some sense, right? You have order n square many of diagonal ones, and in fact, even if I put 0 on the diagonals, nothing does it, usually changes for these problems.
So this 2 is by design or by?
Yeah, the 2 essentially, we do it because the intuition is that if I took a matrix G, which was not necessarily symmetric, but let's say it had entries Gij, where Gij were IID normal 0 1 over n.
Oh, you sum them together.
Then if I look at G plus G transpose by root 2, then this would have the same distribution as W. That's why I take it to be 2 over. But the precise variance in the diagonal entries usually doesn't really matter. It's of a lower order. Okay. Okay, so why do I care about this problem? It is a very stylized problem. You know, I definitely don't want to claim that this is a very real problem, but I still think that it captures many interesting settings, you know, that come up quite often in data analysis, and these are idealizations of some real problems. Okay, so let me talk about a couple of motivations. So motivations. So one motivation is in the context of principal components analysis, right, PCA. So PCA is sort of this basic primitive of unsupervised learning, where you have data and you essentially believe there is some low dimensional structure in the data, and the way you try to recover it is to basically, you know, take the top principal components, project the data down in those directions, and get an approximate low dimensional representation for your data. So this is essentially, you know, one very simplified setting in which you can see this phenomenon. You have your data that you observe. It is some low dimensional structure plus noise, and you're trying to recover this low dimensional structure from the data. Right? And what this problem does essentially is that it goes one step beyond, and it says, suppose I have some additional information about my low dimensional representations, how can I exploit that? So here what you have in addition is that not only do you know that your data is a rank 1 matrix plus noise, you know that the entries of the spike are plus and minus 1, and they are kind of uniform. Right? So this is side information or background information that you have, and the question is, can you really exploit that when you're trying to recover this low rank representation? Right? So recover sort of low rank representation given background information, right? So that's one motivation, at least to me, to look at this problem. And the second motivation, so the reason why I refer to this as the Z2 synchronization problem per se, is this general problem which is referred to as group synchronization. This comes up a lot in chemistry and in other areas. The general idea is that, so here is my attempt at explaining the problem. You know, I can assure you, if you look at the real papers, they will be much more interesting. But the idea is that somehow you have these cameras that are located, but you don't know their exact locations. Instead, what you can see is a picture of an object that has been taken by a pair of cameras. Okay? And you see a noisy version of this, and you get a bunch of these images. And what you want to do is to recover the relative positions of these, you know, of the cameras. Okay? So roughly that's sort of one problem, and an abstraction of that is that you have some group G. So you should think of the group of rotations, you know, when you're thinking of the camera example. And what you get to observe, so you know, you have these unknown elements sigma I in the group, and what you get to see in the group synchronization problem is a noisy measurement of sigma I inverse sigma j. So this is the relative position of the two cameras, right? And the question somehow is, how do I recover the relative orientations from these measurements, right? And so this problem is like a very simplified version of that, where I take my group to be the group of two elements plus and minus 1 with mod 2 addition. And I take the noisy measurement to be literal, and I take it to be additive Gaussian noise. So this is a very simplified version of the problem. But what I'll try to convince you of today and over the next few days potentially is that this simple formulation already shows a number of very interesting features and gives us a lot of new insights, which I think can be practically useful. Okay? Yeah?
Is the noise model always assumed to be Gaussian, or if we can work with other noise models?
Right. Oh, okay, so good. So there are two aspects to that question, right? One is, if the noise is additive, do I need it to be Gaussian? And the second question is, does it need to be additive noise? The answer, of course, to both is that no. This is like an idealized setting that I'll consider, and I'll come back to it potentially, I think, on the very last day, because I think there is a lot of work to be done going beyond Gaussian noises. I believe that if the noise is additive, then having Gaussian noise doesn't really matter all that much, as long as your noise has sufficiently light tails. But for example, if it's heavy-tailed noise, then I think the situation will be different. And of course, if it's a different noise model, then things usually change, but there is some hope to reduce things back to sort of this setting. But you're right that more general noise models definitely make sense, and they will, in certain cases, show other behavior. So that's definitely relevant. Yeah.
Following this question, so look at this really related to robust principal component analysis. If you consider the noise is kind of sparse elements, so will you make connection between these two?
So when you say robust PCA, what are you trying to be robust to?
Maybe corruptions in your data, that this W matrix becomes a sparse.
Sure. Right. So you can add those on top of this, right? Like you can say, okay, here I assume that the matrix M is entirely given to me. You can say, oh, I don't see the entire matrix M, I only see some entries, or that some additional entries get corrupted with additional noise and things like that. So that's, I think, an additional layer that you can add on top. Okay. Okay, great. So let me add one other remark here, which is that it's actually very helpful to think of this problem as a Gaussian equivalent of the block model. Okay, and that is actually one perspective that has been really useful in understanding these problems. So I just want to add a remark that these two problems are actually quite intimately connected. Okay, so I want to remark about the connections between the block model and Z2 synchronization. This will be, at a more informal level, so I won't make very rigorous claims here, but this connection really exists, and it's conceptually very helpful. Okay, so the way to see that these two problems might be quite similar to each other is that, let's say, I take A to be the adjacency matrix, of the graph G that I had, right? So recall that the adjacency matrix of a graph is an n by n matrix. I put in 0 or 1 on the ijth entry if there is an edge connecting the ith and jth vertices, right? That's what I do. And I define the parameter d to be a plus b on 2. This turns out to be the average degree of the graph. So the point is, if I look at the matrix A minus d over n 1 1 transpose, so 1 is the vector of length n with all entries equal to 1. So you can check that this can be written as A minus B over n sigma sigma transpose plus A minus expectation A. Okay. This is just direct algebra. I did not do anything. This you can just check. And now you already start to see the conceptual similarities between the two problems. You know, if you had this matrix, it's really a rank 1 perturbation or rank 1 matrix plus additive noise. This is mean zero noise. The difference, of course, between this particular noise model and the Gaussian noise that I had is that in the Gaussian case, all the off-diagonal entries had the same variance. Here, that is not the case, right? So if I look at this matrix, essentially, you know, the ones in this particular block, they are Bernoulli with parameter a over n. The ones here are Bernoulli with parameter b over n, right? So naturally, even after I center the matrix, the variances are not exactly of the same order. But turns out, okay, this is not really that much of a difference. But the only remark that I wanted to make here is that there is a lot of conceptual similarity between these two models. Both are, you know, once I translate the graph problem into questions about its adjacency matrix, it's basically always a rank 1 matrix plus noise. Okay? And so, okay, let me keep it at this. Okay, any questions about this? Right. Let me talk about one final example before I start talking about the statistical problems. Okay, let me work on top of this. Let me keep this. So let me talk about community detection. Now is when I use a different color. So let me talk about community detection with node covariates. Okay. So this is a variant of the first problem. I want to talk about this because it presents a setting where you want to combine information from different data sources about the same underlying structure. Okay? So what is the idea here? The idea here is that in addition to the graph, you also get to see a vector bi so how should you think about this? Think about a setting where, you know, you get to see a social network. The nodes represent individuals. You can see how they interact with each other. So you can see, you know, who interacts with whom on your social network. But in addition, you also get access to demographic information about every individual, right? So you get, let's say, you know their age. Let's say you know, where they work, some things like that. Their educational qualifications. You have some such characteristics that you see at every node, right? So this is an additional information that I give you. Now, in the first case, in the community detection example, all I was telling you is that you have access to the graph and you want to recover this underlying partition or this clustered structure based on the graph. Naturally, you would expect that if you had this extra information at each node, you should be able to combine that with your graph and do better. Right? That's the intuition. So how do we set it up formally so that the node covariates give you additional information, right? So what I'll assume is exactly this setting for the graph. So the graph will come from the block model as I have described before. But in addition, now I will do the following. I will assume that there is a vector u, which is a p-dimensional Gaussian, right? And the bi's that I observe are basically sigma iu plus zi over square root p, where the zi's are id normal 0 identity, and everything is independent. Okay, so what is the intuition here? The intuition, and okay, mu is a positive constant that is fixed. So the intuition is that, let's say my sigma is +1, then I get to see this vector bi, which is centered around some scaled version of u. So I get some data cloud here. Whereas if sigma is -1, then I get to see some data cloud here, right? So the intuition is that there is some latent cluster center u. For the vertices that are in group 1, I get a noisy observation around u. Whereas if sigma is -1, then I get to see a noisy observation around -u. And the parameter mu essentially controls the separation between the two clusters, right? So if mu is large, then I get a lot of information. If mu is small, then I don't get any information. Right? So this is, a variant of the vanilla community detection problem, where I have these two sources of information, and my target, and I know I've been keeping this vague, but I'll move on to this immediately, but would be, that if I define a matrix B where I stack all these vectors as columns, so that this is P by N, is combine the graph G with B to recover sigma. Okay, any questions about this? Yeah?
I understand this as a combination of SVM and Gaussian mixture.
It is a mixture, right? But the common thing here is that I use the same shared underlying latent structure. But it is really a mixture of the two.
But just maybe following up on the same thing, I guess you want to say if I just had the second information, then you can do recovery some which way. And if you just had the first information, you can do with some parameters. If you're both, you can do better. Yeah.
Exactly. So that's what we'll see. Exactly. Right. That if you just had access to the first source or just to the second source, individually you can do recovery in certain cases. But even in this very simplified setting where I mash the two sources together, in fact, there exist strategies that will let you combine them judiciously so that you can do non-trivial recovery even when any one source will not let you do something non-trivial.
Will you be pointing out the precise thresholds where recovery is impossible statistically?
Yes, that's my plan for the rest of the lecture today. Great. Okay, so I think right now is the time when I should talk about the specific questions and what the thresholds are. Okay, so what are the statistical questions of interest? Okay, so I'll talk about 3 questions. One is something that I'll refer to as detection, recovery, and I'll also talk about optimal recovery. Okay. So these are the 3 questions that I'll talk about. Let me elaborate more on these. So let me first start with the detection question. So the detection question in some sense is a very basic question. You say, okay, I have some data which is essentially signal plus noise in some sense. My eventual goal is to recover the signal, but first I need to be able to determine if this is signal plus noise or just pure noise. Like, is the signal even present? So is the signal present? That's kind of the question, right? And we usually formulate it in the context of a hypothesis testing problem, right? So let me formulate this in the context of Z2 synchronization. So in the Z2 synchronization case, we formulate it as a hypothesis testing question where lambda is 0 versus lambda is positive, right? So recall that in this example, the matrix that we see was, right? So under the null, lambda is 0, so that what you see is basically pure noise. Under the alternative, lambda is positive and you have some signal, right? And so how do we formalize this question, right? So when do we say that detection is really possible? So I'll talk about this notion of consistent detection. So I need a hypothesis test, right, to distinguish between these two things. So let's say I have a sequence of tests. This is a sequence of hypothesis tests. And so we say that consistent detection is possible if there exists a sequence of tests Tn such that, let me write something and then let me parse it. So this is my type 1 error, right? So this is the this is the probability that I end up rejecting the null hypothesis, even though the data is actually from the null. And this is my type 1 error, or type 2 error, right? So this is the other thing. My data is actually from the alternative, but I failed to reject the null. So essentially what I'm saying is that I'm really able to say with confidence that there is signal in my data, if I have a sequence of hypothesis tests that essentially make 0 errors asymptotically, and n generally represents the size of the example that I have. So in the context of Z2 synchronization, n diverging essentially means that I see a sequence of larger and larger matrices. Okay. One can formulate similar questions, for example, in the context of community detection and the other things as well, but this is what will be the detection question for us. Okay, questions? Okay.
Sorry, I'm confused about the end. So you're saying that you have a sequence of
problem instances,
problems,
yeah,
that are larger and larger,
right?
And you have a family of hypothesis tests that you operate for larger and larger.
It's the same hypothesis, right? Because the entire problem is indexed by just one parameter lambda.
I mean the tests.
The tests work on, yeah. So Tn looks at the matrix M, which is of size n by n, and decides whether to reject or not, right? So the Tn's essentially are tests that work on matrices of different instances. But for example, typically this can capture settings like, okay, if I decide to reject, let's say by summing over all the entries of the matrix, Tn could refer to that test which is applied to the matrix of size n. Right. Okay. Right. So that is detection. Let me talk about recovery. So recovery is really, exactly what it sounds like, right? Can we recover or estimate the signal? Right. Now, how do we formalize this? Let me formalize it in the context of the community detection problem. So I'll work in this, scaling regime for the probabilities. So note that if I have a graph drawn from the block model, and if my edge probabilities are of order a over n and b over n respectively, and if a and b are constants, then this implies if I look at the number of isolated nodes in the graph, then this is actually order n with high probability. So for example, to convince yourself of this, you can look at a specific vertex, look at the probability that it is isolated, right? So it has none of its neighbors, and then you can look at, let's say, the expected count. And in fact, one can prove a lot more. In fact, this has a Poisson distribution in the limit, but in fact, this is the case. And if this is true, then of course, for an isolated vertex, you can't really recover its community assignment non-trivially, right? It has no connections whatsoever. So you get no information about this specific vertex. So the best thing that you can do is basically do a coin toss for isolated vertices. And therefore, for example, you can, in this particular scaling regime, it doesn't even make sense to say that I want to recover all the communities exactly accurately. That will not just be possible, right? So as a result, we naturally become a bit more conservative, and we say, fine, can I do better than random guessing, right? Can we do better than random? Right? And we formalize this through this notion of weak recovery. So we say weak recovery is possible if there exists some estimator sigma hat for my underlying vector sigma, such that if I look at 1 over n absolute value, this is my inner product between the two vectors, this is greater than some epsilon with high probability, right? So just to parse this a bit more, if I were guessing randomly, then 1 over n, this inner product, would be basically 0. So I just want it to be bigger than some epsilon. So I just want to do better than that. Okay. So this is my recovery question. So you can formulate this question in under both these problems, right? And I will say weak recovery is possible, you know, depending on the data model. But this is the specific question, right? The question makes sense for both variants of the problem. The thresholds will change depending on what the problem is. But this is the basic statistical question. Right. And finally, let me talk about optimal recovery. Before I do that, let me make one comment. And this is kind of going back to why I assumed this particular scaling on the probabilities. So of course, you can imagine that if my graph were more dense, so for example, if Pn and Qn were constants, then I would be able to do a lot more, right? I wouldn't have isolated edges, I wouldn't have isolated nodes, sorry. And so I could try to do more. And in fact, in that case, weak recovery is not the right question. In some sense, people can do exact recovery, and people have looked at all sorts of variants of community detection on more dense graphs and things like that, right? So I won't go into that. In this particular scaling, weak recovery is kind of what makes sense, and I'll restrict myself to it. But I wanted to make it clear that all the other variants have been explored. If you're curious, I'd be happy to share specific pointers. Let me just make one comment about optimal recovery before we take the break. So, and this goes back to the question Debankur posed, which is, okay, why did I, you know, assume that the underlying parameters are drawn from some distribution, right? I could have as well assumed that these are, you know, fixed parameters that I'm trying to recover. So what it helps me to do is that it helps me ask a finer question. So here I can pose the question, okay, I can do weak recovery maybe. But the way I have set up all these problems, these are in some sense, you know, problems where my underlying signal comes from a prior distribution, right? So these are completely Bayesian problems. And I could ask, okay, going beyond weak recovery, can I do Bayes optimal recovery, right? So the question is, can we do Bayes optimal recovery? And turns out this is quite challenging to do using efficient algorithms. This will be sort of a part of our focus for the third lecture, right? So what I plan, so we'll take a break now, and after we return, I plan to address Santosh's question, which is, okay, I'll talk about what are the fundamental thresholds in these examples, and I'll discuss some information theoretic ideas to actually prove, you know, what are regimes where nothing really can be done in the context of the detection question. Tomorrow's lecture will be focused more on the positive side, so coming up with algorithms that can, you know, do detection and recovery. The third lecture will focus a bit on optimal recovery, right? So that's kind of my plan moving forward. And I should say that, you know, in this entire scheme of investigations, one issue that I have kind of skirted under the rug is that, okay, it's not really, you know, satisfactory, for example, if I tell you that there is a sequence of tests, but that involves exponential computation, right? So if it turns out that you can actually detect everything consistently, but to do that you have to spend exponential time in terms of your input size, right? So there are, of course, questions that, like, okay, when can you actually do detection, recovery, and optimal recovery using efficient, let's say, polynomial time algorithms? So that's essentially an intrinsic part of these questions that are separate from the information theoretical statistical questions here. There has been a lot of progress on these questions, you know, by many people in the audience here as well. And surprisingly, it turns out that in certain cases it is conjectured, and there is some increasing evidence that even though information theoretically something could be possible, it might not be possible in let's say, polynomial time, right? So we'll touch upon this side of things briefly in the third lecture, but yeah, that's sort of my plan. So let's take a break for the moment, and, you know, let me know if there are any questions. So let me first talk about some of the results that have been established for these models. So what are the fundamental statistical thresholds, right? And we'll then talk about some techniques to prove, you know, some of these results. So let me first talk about the result for the for community detection. So when I state this, I feel obligated to actually mention some of the references. So the formal results here are due to Moselle, Neiman, and Sly in a bunch of papers starting from around 2013 and so on, and then also by Laurent Massoulier around 15, I think 14, 15, and others, right? So what is the result? The result is that you define D to be A plus B on 2. This is again the average degree of a vertex, and you define the parameter lambda to be A minus B on square root 2 A plus B, right? And the result is, okay, so let me state it in two parts. The first part is for detection. So I'll fix myself always in the regime where D is bigger than 1. This is related to a classical phenomenon in the context of random graphs. So if D is less than 1, then in fact, you know, if you look at your vertices, everything is in very small groups. You know, there is no global structure in the graph, and you can't really do anything non-trivial. So this ensures that there is a so-called giant component in the graph. So what it typically says is that if you look at the set of vertices, then there are order n vertices that are connected to each other, and this is sort of required. Then you can kind of propagate the information and do non-trivial recovery. So I'll restrict myself to this case. Then consistent detection is possible if and only if lambda is bigger than 1. And the recovery threshold in this case is actually the same. So weak recovery. So weak recovery basically at the same threshold, right? So the threshold in this case for both problems is the same. Actually, they will be the same in all the examples that I talk about, but in principle they could be different. That's why I state them in this form. For most of these kind of regular well-behaved problems, the thresholds for detection and weak recovery coincide. To see sort of some intuition for this parameter lambda, note that, you know, if A and B are very different, then you get more signal, right? That makes sense. If A is much bigger than B, then you have like the within group connections are way denser than the across group connections. So you would naturally expect your problem to become easier. And the scaling here, so if you think of D as your average degree, then essentially this is kind of like an SNR kind of parameter, right? This is your normalization in terms of the fluctuation, right? And so it turns out there is a sharp threshold in this problem. If lambda is strictly bigger than 1, then you can do detection and weak recovery. If lambda is strictly less than 1, you can't.
So what do you mean by consistent detection?
Yeah, this is what I had defined, sorry. So consistent detection is when like asymptotically both type 1 and type 2 errors would be 0. So I don't make errors of either kind. Yeah.
So if and only if, so that means that if it's below you cannot, that's a negative result.
Yeah.
And then if it is above, how do they prove this result? They actually present an algorithm, potentially.
Yes. So that's what you would have to do, right? You would have to. So I'll talk more about the positive direction tomorrow. But specifically for each of these questions, there are two parts. You have to prove a negative result, that you can't do these problems below this threshold. And you need to come up with a positive result, which is an algorithm, potentially exponential time, which shows that above lambda bigger than 1, you can do this. Right? So I'll talk at length about the positive side of things tomorrow, but this is the main result. Let me state a similar result for Z2 synchronization. Here the references are less clear because the problem per se has been looked at by many different people. But again, recall that the matrix is lambda over n, right? So the reason why I use the parameter lambda here is that the thresholds then will coincide and things look consistent. So in this case again, consistent detection is possible if and only if lambda bigger than 1, and similar for weak recovery. Okay. So for the detection question, I think there are many papers that looked at this. There was one paper that was by Perry et al. around 2015, I think. I might be getting this wrong, but I think even before that, there were other papers by, there were other papers by Montanari, Zaytouni, and Reichman. Also Banks et al. So there are many different papers that kind of looked at this problem in slightly different motivations around the same time. So all of this happened, I think, around between 2012 and 2015. The weak recovery answer actually just comes, like the positive part of the algorithm essentially just comes from something like PCA. So we'll see this tomorrow. It actually goes back to random matrices and is a bit older. Okay, and then finally, let me state a result for, let me state this as contextual block models. So this is the setting where we have the additional node covariates. So in a couple of joint works, so one was with Yash Deshpande, myself, Elkanan Mosel, and Andrea Montanari. We looked at this around 2019, I think. And then I had a follow-up paper with Chen Lu on this around 2020. I think this was 18. Okay. So around these times. And there is also some other results by Baoyan and Purnamrita Sharkar, but they look at it in a different scaling regime. So I won't quote that today. But so what we did is that in addition to this, we made an assumption of a high dimensional asymptotic. So we assumed that both P and N actually grow, but in a proportional sense. So this converges to some 1 over gamma. Right? And then our result is that, so let me just state it this way, that detection and weak recovery possible if and only if lambda squared plus mu squared on gamma is strictly bigger than 1. Okay. So you kind of see the effect of having these additional covariates. This goes back to what Mohit was asking, in that, you know, if you just had access to the graph, then this result essentially tells you that the right threshold is lambda square equal to 1. What the last result essentially tells you is that if you had access to both sources of information, if you combine them, then you can in fact do it as soon as lambda squared plus mu squared on gamma is bigger than 1. Right? So there is some improvement if you combine the two sources judiciously. Yeah.
What is the intuition for Z2 synchronization like you had for community detection?
So intuition for what?
For why lambda should be greater than 1?
Yeah, it's kind of the same intuition, right? In that, like, you have a rank 1 matrix plus noise, right? If you look at the operator norm for the signal part, then it depends on lambda. So the larger lambda is, the larger your signal is. So turns out it's sort of exactly at 1. Okay. Okay. Do the results make sense? Okay. So what I plan to do for the rest of the lecture today is to talk about some information theoretic ideas and statistical ideas that can prove, that can help in establishing the negative side of the detection questions. Okay. So the specific question, let's say, that I'll focus on is for the Z2 synchronization problem. If lambda is strictly less than 1, then I cannot do detection consistent detection, right? That's what I'll try to prove. There's a similar set of tools for weak recovery, but I'll just focus on detection for the time being. So to do this, I'll need this notion of contiguity. So this is contiguity. Okay, so let Pn and Qn be probability distributions on the set Xn Fn, right? So I have two sequences of probability distributions on the same sequence of spaces, right? And we say that the sequence Qn is contiguous to Pn and I'll use this notation for this, right? If Pn of En goes to 0 implies Qn of En also converges to 0, right? For all sequence of sets En where En is of course in Fn. Okay. So let's parse that for a moment. So I have a sequence of spaces, Xn, and I have two sequences of distributions, Pn and Qn. So for each n, imagine a space Xn, Pn and Qn are probability distributions on that space, right? So contiguity is a statement about the two sequences, right? It's not a it's not a statement about things at a specific n. What this is saying is that suppose I have a set of events En such that Pn of En is actually converging to 0. This will always imply that Qn of En also converges to 0. Right? This is what contiguity is. Roughly, you should think of this as follows. You should think of this as if there is a sequence of events that is very unlikely under Pn as n goes off to infinity, then it is also unlikely under Qn. Right. Okay. Any questions about this? Let me say a couple of things. Right now, this might appear very abstract. You might be like, okay, we were talking about specific examples. Why are we suddenly talking about this abstract notion? We'll connect it to hypothesis testing in a moment. But let me just say that if Qn is contiguous to Pn and Pn is also contiguous to Qn, we say Pn and Qn are mutually contiguous. Okay. Okay, so what is the connection of this with hypothesis testing, right? So let me again recall the detection question for Z2 synchronization, right? So I have the matrix M, which is lambda over n plus noise, and my null is lambda is 0 versus lambda is positive, right? So what I will do is that, note that here implicitly I'm working with a sequence of probability distributions, right? At step n, I have this n by n matrix that I observe, and either it's from the null or from the alternative, right? So I'll talk about the null sequence as Pn and the alternative sequence for a given lambda as Qn. Right? That's how I will apply this notion. Make sense? And the important lemma is that in this setting, if Qn is contiguous to Pn, then consistent detection is impossible. So this is how you would go about getting a negative result, right? So you have two sequences of distributions on the same space, on the same set. If you can prove that Qn is contiguous to Pn, then you know that you will not be able to distinguish between them consistently, right? And the intuition exactly is as follows, right? Like, if you imagine a hypothesis test that looks at some outcome and then rejects the null, that's basically like its decision is based on whether your outcome is in a specific set. So that's your event, right? So for consistent detection to be possible, really it has to be the case that there needs to exist a sequence of events such that Pn of En goes to 0, but Qn of En actually goes to 1 or something, right? But contiguity exactly rules this out. So if the two sequences are contiguous, you don't expect consistent detection. Okay, great. I will not prove this. I'll actually leave this as an exercise. It's actually a relatively direct result from the definition, but I'll skip this. So the main question that comes out is that I want to therefore prove, let's say in this particular setting, that Qn is contiguous to Pn as soon as lambda is less than 1, right? That's what I want to prove. How do I do that? That's kind of the question, like, okay, the definition makes sense, but unless I have some easily checkable condition to prove contiguity, I can't really do anything with it. So that's where the second lemma comes in. So it says that if EPN of dQn dPn squared exists and remains bounded, as n to infinite, then okay. So here is our checkable condition, right? It essentially states that if you can have, the likelihood ratio between Qn and Pn, if this exists and if its second moment is finite under Pn uniformly as n diverges off to infinity, then in fact Qn is contiguous to Pn. Okay, and I'll also skip this, but this is the condition that we need. Okay, and any question on the notation here? So EPN refers to the fact that I'm evaluating the expectation under Pn, right? And dqn dpn is the likelihood ratio between the two distributions.
Sorry, this might be jumping ahead of.
No, no, please.
So the converse of this, so if this is in fact, let's say, unbounded, this ratio,
right,
this chi-square, then would you expect at least statistically it should be possible to always distinguish, right? Yeah.
Right. So it won't come down exactly to the moment of this, but exactly like in we always do the likelihood ratio test, right, between the two things, which is basically like look at the likelihood ratio. If it's large, then reject it. So for example, if it's very large, with some non-trivial probability, then you should be able to distinguish between the two.
In some sense, if it's possible, the likelihood ratio
should always pick it up. But implementing the likelihood ratio test might not be computationally feasible. But yes, if one could analyze it, then that would be the best test. But here, this is reducing it down to the second moment just of this random variable. Okay, so okay, so let's do this calculation in this case. Okay, so I did this yesterday and I hope I have all my calculations correct, but if something is buggy, please feel free to catch me. Okay, so here is our theorem that I have the matrix M, which is lambda on n, Pn is basically the distribution under the null, Qn is the distribution sequence under lambda. Then if lambda is less than 1, then the sequence Qn is contiguous to Pn. Right? And we'll prove this essentially by applying the second lemma here. Okay, so what do I do? So let's do the proof. So suppose I now look at dqn dpn, right? What is this? So note that the sequence Qn also involves this latent vector sigma, right? So the likelihood ratio turns out to be so I have a bunch of Gaussian factors that will cancel, right? Because the variances of the noises are the same in the two models. Okay, so let's parse that for a moment, right? So I know that the matrix Mij, given the vector sigma or V, is basically a Gaussian with mean lambda over n Vi Vj, right? So first I look at the conditional likelihood, which essentially looks like e to the minus n over 2. The n factor here comes from the fact that I have the variances of the Gaussians are 1 over n. And then the entries above the diagonal are all independent. That's why I have a sum here. And then I marginalize over you know, the effect of choosing the vector v. Okay, I need to have a 1 over 2 to the n here. And this is the likelihood under the null. Now let me say there is one thing here which is specific to this problem, which is that I'm summing only over I less than j. Of course the matrix is symmetric, so I less than j and I bigger than j are the same, and I therefore don't need both of them. That's one. The second thing is you can say, okay, why don't you have I equals j terms here? And that is actually special to the Z2 synchronization problem, because well, yeah, okay, I should have I equal to j as well. Let me have I equal to j. Okay. But okay, no, this is why I was kind of trying to avoid it. I need, if I go for the I equals j terms, then my variance will be different, right? My variance will be, you know, 2 over n. So things change slightly. So it will be n over 4 sum I from 1 to n mii minus lambda over n vi squared. This will be minus n over 4. Okay. Does this make sense? Okay. Okay, so let's simplify this a bit. So this is 1 over 2 to the n. Let me write this as expectation over v. This denotes the expectation over the uniform choice of v on the hypercube of. So if I expand these out, then the quadratic terms essentially will cancel, right? And I will get e to the, okay, let me check what I expect to get. Maybe first let me do this. So let me write this as e to the negative n over 4 sum I not equal to j mij minus lambda over n vi vj squared minus n over 4 sum I right. So all I did here was, you know, I made this n over 4 and then summed up things instead of I less than j over all I not equal to j. Nothing really changes because the matrix is symmetric. So this is in fact EV of e to the negative n over 4 right, and then this is EV of, okay, so e to the, so the Frobenius norm of m squared, that term will cancel in the numerator and the denominator. So I will have one term from the cross product, which is right, so this will be lambda over 2 m v transpose, and then there is a negative lambda square over 2 over 4n times I think this is okay. So this will be right. Okay. So I just expanded out the terms. I hope I got all my coefficients correct. So lambda squared over n squared, 1n cancels. Yeah. Okay. And this is essentially the matrix inner product. So trace of AB transpose. Okay. And VV transpose, this is VV transpose VV transpose, so that's n square, right? So that this term I think is just this. Make sense so far? Any questions? Okay, so let me talk about this. So now, so far what we did was that we wrote down what the likelihood ratio is, and we got an expression for this. It involves a marginalization over this choice of V. So what I'm expected to do now is to look at what is dqn dpn squared, and then I'm supposed to take its expectation under Pn, right? So now that's basically this expectation squared, right? So one thing I can do, and this is sort of the trick that I really want to talk about, is that I can write it as a joint expectation under two independent vectors sampled from the hypercube of e to the lambda over 2 m v1 v1 transpose plus v2 v2 transpose, and then minus lambda squared n over 2. Okay, that's all that I did here. Now the advantage of this is that if I have to calculate what is EPN of dqn dpn squared, now I have to take an additional expectation here over Pn, right? But I can interchange expectations, linearity, Fubini, so that this is expectation under V1, V2 of expectation under Pn of this entire thing. Right? So I flipped the order in which I take the expectations. Okay? Make sense? Right. Now comes the point where things are nice. Note that when I'm taking the expectation with respect to Pn, the only thing that depends on Pn is this matrix M. And in fact, this is why I wanted to take the expectation under Pn, because under Pn, M is basically distributed as pure noise. So under Pn, M has the same distribution as W, which is pure noise. Okay? And if you think about it, this is essentially calculating the moment generating function of some Gaussians, right? Because these Mij's, at least the ones above the diagonal, are independent Gaussians. You're just basically calculating some moment generating function of independent Gaussians, right? So let me not try to do this calculation live, because I'm sure I'll get some factors off. But what will come out of this is that if you look at EPN of dqn dpn square, this will be essentially the expectation over v1 v2 of e to the lambda square n over 2 okay. So this is the inner product between v1 and v2, and okay, this is direct algebra. Here I just calculated explicitly what this expectation is. Okay, so if you believe me up to this point, then all that I have to do is to prove for you that this expectation actually remains bounded as long as lambda is less than 1, right, as n goes off to infinity. That's all. Okay? And there are many different ways to do it. I'll just sketch a very bare bones and direct approach that works for the zeta synchronization case. So in this case, note that you have two vectors v1 and v2 that are sampled uniformly from the hypercube, right? So if I look at the inner product, this is just the sum of these entries. Right? Actually, I think I might be missing a 1 over n factor here. I think if it's n here, then it might be the normalized inner product. I can check and let you know, but I think it might be this instead of that thing. I think that's the right thing. Okay. But the idea here is that now, if you look at these terms, if v1 and v2 are sampled uniformly, then each of this term is IID, and it's either +1 or -1, right? So you can exactly write down what is the distribution for this object. So the probability that the inner product of v1 and v2 is m. So this is m essentially means that if there are t terms which are +1 and n minus t terms that are -1, then it essentially means t minus n minus t is equal to m, which is equivalent to saying that t is m plus n over 2. Right? So I can write down an explicit binomial formula for this. Right? And once I write it out, essentially it's a matter of plugging it back into this exponential moment and proving that if lambda is less than 1, then that remains bounded. Okay. So now can use this to check that expectation over v1 v2 of e to the lambda squared n over 2. I think this object remains bounded for all n sufficiently large. Right. So this is sort of how you would go about it, right? Generally you can do something a bit more sophisticated, but this is kind of a very bare bones direct approach for this problem. Okay. So this contiguity idea generally, okay, let me finish off here and make one remark. This contiguity idea turns out to be very useful whenever you're working with problems where there is additive Gaussian noise and things like this. If you're working on sort of sparse graph problems or graph problems generally, then directly proving contiguity can be more challenging. So in things like community detection, you need sort of some slightly different ideas, but you still prove contiguity. That's what you want. But you know, going at it via this second moment of likelihood ratio idea, that works better for the Gaussian cases. We have a few other tools that can be used to prove contiguity, but this general notion is very important for proving lower bounds for detection. Okay? There are some similar other ideas, statistical ideas, that can be used to prove lower bounds for weak recovery. But yeah, these are sort of similar flavor, so I won't really go into that. Okay? So my plan tomorrow is to talk more about the positive side of things. I'll consider the same examples, and I'll start with sort of algorithms. Okay. Yeah?
I'm sorry, I didn't get how did you get the first right from the...
This one, right?
Yeah, how did you get...
Yeah. So here all I'm using is this fact, right? So imagine I have some function of x, right? X is some random variable. And I have expectation of f of x. And then I'm squaring it, right? So that is basically expectation of f of x times expectation of f of x. Great. What I can do is that I can take two IID copies and write it this way, and then that essentially becomes expectation of f of x1 times f of x2. That's what I did here. I had this expectation squared, took it over two expectations, merged everything. Okay, I think I'm right around time, so I'll stop here.